I'm going to post example 6-3 on Blackboard. You can take a look at it whenever you get an opportunity to do so. It's very similar to example 6-2, and so I don't want to bore you by going through it in depth on this video, but I do think it's worth taking a look at and just seeing another example of how you can calculate the plastic section modulus and then the plastic moment capacity of a singly symmetric shape. Alright, so we've talked about how to calculate the plastic moment capacity of a beam and flexure, but we have not talked about how AISC says to handle it. So for a continuously laterally supported beam, AISC says that the nominal moment capacity is just equal to the plastic moment capacity, which is equal to FYZX. So this is exactly what we have just gone through. And this is equation F2-1. The resistance factor for flexure is 0.9, so that should be easy to remember since it's exactly the same as it was for columns. So as evidenced by the equation number here, AISC covers flexure in chapter F of the specification. So this is chapter F. It's going to be one of the longer and more detailed chapters within this spec, and it's divided into 13 different sections. One handy way to navigate this particular chapter is to use table user note F1.1. And this will make a little bit more sense in a couple minutes when we start talking about the local buckling limit state for flexural members. But this table can be used as a roadmap for figuring out where the design provisions that you need to use are located within chapter F. So we'll revisit this in a little bit. So about local buckling. Local buckling is the next limit state that we're going to be discussing. When we deal with local buckling for flexural members, we're looking at 3 different categories of local buckling susceptibility. And these are going to be based upon width to thickness ratios in a similar manner as how we handled that for compression members. So lambda is just our width to thickness ratio. This could be for any element in a cross-section, such as a flange, a web, leg of an angle, stem of a T, so on. Lambda sub P is going to be a value that we're going to calculate using the tables in chapter B of the specification, table B4.1. And lambda sub P is the upper limit for the compact category. So if you calculate a lambda value for an element in the cross-section and it's less than lambda sub P, that means that portion of the cross-section is compact. Lambda sub R is the upper limit for the non-compact category. So whereas for columns we really had 2 classifications, non-slender or slender, for beams we're going to have 3 designations: compact, non-compact, and slender. So if lambda is less than lambda sub P, the element is classified as compact. Compact just means stocky. If the lambda you calculate for the element you're looking at is in between the limits of lambda sub P and lambda sub R, that element is non-compact. And if the lambda that you calculated is greater than lambda sub R, It's slender. So this is the solution space for local buckling. I have slenderness of the element on the x-axis. It's shown here for a flange, df divided by 2tf, but this plot would look similar if we were looking at slenderness for a web, or if we were looking at slenderness for any other type of element in a cross-section. On the y-axis, I'm plotting nominal moment capacity. And our solution space is divided into those three categories: compact, non-compact, and slender. The dividing lines between those three regions are lambda sub p and lambda sub r. You'll notice for a very compact shape, the maximum value that we can reach is the plastic moment capacity. If the cross-section has elements that are non-compact or slender, you're never going to be able to reach a capacity as high as the plastic moment. It's going to be limited by the local buckling capacity. The capacity will be less than the plastic moment value. So on the boundary between non-compact and slender, we have this value 0.7 FYSX. This is the same as saying 0.7 times the yield moment. And where this 0.7 comes from is a reflection of the presence of residual stresses in cross-sections. So here's a photograph that we looked at before with pertaining to the plastic moment, but here I'd like to focus on the local buckling that's occurred in the flange. So you can see that the local buckling has occurred in a half sine wave, and this is a typical form of local buckling. You can also see that this corresponded with some local buckling of the web. It's a little bit tougher to see, but the web has actually buckled out of plane in this case. This is another good photograph showing local buckling of the flanges in particular. You can see that the flange has buckled like so. And so it's our job as designers to make sure that the capacity of a cross-section reflects its susceptibility to local buckling. Okay, we've got a couple of more examples to go through, the first of which is example 6-4. So this will be the first example that we've gone through in this lesson plan where we use the AISC specification to determine whether or not a particular beam is sufficient to support a series of loads. So we're looking at a W10 by 60. It's made out of grade 50 steel. It's being used as a simply supported beam that's 25 feet long. The beam supports a concrete floor, and the concrete floor is constructed such that it provides continuous lateral support to the top flange of the beam. The floor weighs 460 pounds per foot, and the service live load that the beam supports is 500 pounds per feet. So we're going to determine if this W10 by 60 is sufficient to support the loads. One of the first things I like to do when presented with a problem such as this one is to make a sketch of what is going on. So we have a beam that's simply supported. The beam is 25 feet long. It's a W10 by 60. It supports a floor dead load of 460 pounds per foot. And it also supports a service live load of 500 pounds per foot. I'm going to make a minor edit to the problem statement here, because the intent of this 460 pounds per foot is also to include the 60 pounds per foot of the steel beam. So I'm going to say the floor plus the self-weight of the beam weighs 460 pounds per foot. So this 460 pounds per foot is the total dead load that the beam is supporting. Okay, so first step, we're going to factor the loads. All we have applied are dead loads, so I really only need to be focusing on two different load combinations. The first is 1.4 times the dead load of 460 pounds per foot, which is 644 pounds per foot. And the second is 1.2 times the dead load, 460, plus 1.6 times the live load, 500 pounds per foot, which is 1,352 pounds per foot. So load combination number 2 is the one that controls. So that is the factored distributed load that we're going to have to design against. From that factored load, I can determine a factored moment, and that's really what we need when we're designing a beam. So factored moment demand. I'm going to sketch my beam again. And this time I'm going to show it with my total factored distributed load. And that was 1,352 pounds per foot. And that's my controlling distributed load after it's been factored. It's always good practice to sketch out the moment diagram. And when we start talking about shear, we'll also make sure that we're sketching out the shear diagram. The moment diagram for this particular loading on a simply supported beam is going to be parabolic, and the maximum moment for this case is going to be pretty easy and familiar. It's W L squared over 8. So my maximum moment is going to be 1,352 pounds per foot times a length of 25 feet squared divided by 8. And that gives me a maximum factored moment demand of 105.6 kip feet. So that is the moment demand that we have to design for. Now the next step in looking at a problem like this is to determine the width to thickness ratios for the elements in the cross section. And what this does is it's going to allow us to classify the shape as being compact, non-compact, or slender. And this is a very important type of criteria so that we're using the correct provisions within Chapter F of the specification. Let's start with the flanges. We'll have to do this for all elements in the cross-section, the flanges and the web. Lambda for the flanges, we would calculate exactly the same way that we would for compression. It's tabulated in Part 1 of the manual as 7.41. But now instead of comparing this against lambda sub r for uniform compression, I'm going to use table B4.1 for flexure and calculate lambda sub p. So let me flip over to my specification And I'm going to scroll back to part B. It might take me a second to find it. Okay, here's table B4.1. Oops. Table B4.1a was for compression elements. So we don't have a compression element any longer. What we have are members subject to flexure. So now we have to look through here and determine what lambda sub p is for the flange of a rolled I shape. And it is the very first row here. Lambda sub p is 0.38 times the square root of E over Fy. So this is equal to, for 50 KSI steel, 9.15. And I don't have to go any further because lambda is less than lambda sub p, so this tells me the flanges are compact. Next, I'll do that same process for the web. Lambda for the web is going to be h over tw. That's tabulated for this shape as 18.7 in part 1 of the manual. And then I need to look up the relationship for lambda sub p again. So I'll flip back to the spec. And now I'm looking for stiffened elements. Here are my stiffened elements. You can see the table is divided into two halves between cases 14 and 15. Case 15 is for the webs of doubly symmetric I-shaped sections and channels. That's us. Lambda sub p is 3.76 times the square root of E over Fy. Lambda sub r is 5.7 times the square root of E over Fy. So lambda sub p is 3.76 times the square root of E over Fy. For 50 KSI steel, this comes out to a value of 90.62. I don't even have to calculate lambda sub r because lambda is less than lambda sub p. So the web is also compact. Okay, so summarizing up to this point, the problem statement told me that I have continuous lateral support, meaning I don't have to worry about lateral torsional buckling for this problem. And for local buckling considerations, the flanges are compact and the web is compact. So since my flanges and my web, my entire cross-section is compact, that means it's stocky enough to develop the full plastic moment so long as lateral torsional buckling is prohibited. So because I have continuous lateral support, I know that there's no lateral torsional buckling, so my capacity is going to be limited by the plastic moment. Right, M sub p. Now, another way of arriving at that very same conclusion is to go back to chapter F. There we go. Design of members for flexure. And to go to user note F1.1. And define the case in here where we have a compact flange and a compact web. So first case, flange is compact, the web is compact. It tells us in the far right column that we should be checking yielding and lateral torsional buckling, and that we should be looking at section F2 in chapter F. Now I know, because we have continuous lateral support in this problem, that I don't have to check lateral torsional buckling. So the only thing that I need to be checking is the yielding limit state, and that just means the plastic moment capacity. So I'm going to scroll down to section F2 in the specification. Here we go. It gives us the provisions for the yielding limit state right here, and it also gives us the provisions for lateral torsional buckling, which for right now we get to ignore because the compression flange of this beam, which in positive flexure is the top flange, is continuously laterally supported. So our next step, calculate the design moment capacity. So I have a compact flange and a compact web. Means I have no susceptibility to local buckling. Because I have continuous lateral support, that means I have no susceptibility to lateral torsional buckling. Therefore, what I need to check is the yielding limit state. And by that, I just mean the plastic moment capacity. This is covered in section F2 of the spec. So let's calculate the yielding limit state. My nominal moment capacity is going to be equal to the plastic moment strength, which can be calculated as Fy times Z sub x. This is equation F2-1. So right there. Yield strength is 50 KSI. You could calculate Z sub x by hand, but luckily for us, for rolled shapes, Z sub x is going to be tabulated in part 1 of the manual right next to S sub x. So if I look up a 10 by 60 in part 1 of the manual, I find that Z sub x is 74.6 inches cubed. So my nominal moment strength is 3,730 kip inches. Since I calculated my factored demand in terms of kip feet, I'm going to convert this to kip feet by dividing by 12. This is equal to 310.8 kip feet. That's my nominal moment capacity, capacity. My factored moment capacity is going to be 0.9 times 310.8 kip feet, or 279.8 kip feet. Okay, so let's look back at our demand now that we know that our factored resistance is about 280 kip feet. I look back at my demand, it was 105.6 kip feet from that point on the moment diagram. So my factored resistance is higher than my factored demand, so my overall conclusion is going to be that the W10 by 60 is sufficient. So Phi-Mn, my factored resistance, was 280 kip feet. It was greater than my factored demand of 106 kip feet. Therefore, the W10 by 60 is sufficient.